You're raising your hand.
Yep. Hello. Thank you, Dave. You commented on some hydrothermal. You had a photo with one showing hydrothermal activity.
Yep.
Was that unusual? And can you explain?
Well, most of the Dolerites were not altered significantly. There were one or two that were, and in general, when they were altered, it was because of the fact that they had xenolith within them. Certainly the ones with the andesite garnet and the boxwood calcite, that alteration was very much along the joint planes. It was very much associated with the xenolith. There was another a part of the basal Sealer and coal seam cliffs, which also had a bit of a hydrothermal alteration. And again, that was associated with a small xenolith near the top of that spill. But in general, there was very little hydrothermal activity within the cells at all. They were basically pristine dolerite.
Okay, thanks.
Thank you, Dave. Hayden, your hand's up.
Yeah,
Oh dear.
Dave, it was lovely to hear about the work that was being done in the 70s. I think, you got in there before I did. This is following on from Liz Aston's question, really. Given the amount of igneous activity that you've been describing from Antarctica, but also the relationships that you were flagging up on the other continents that were attached or sub-attached to each other at the time. So what we're looking at in that phase in the Jurassic were igneous activity that was of similar age, right across from South America through the Karoo in South Africa, and then obviously into Antarctica and Australia.
And India
And India, yeah, precisely. That being the case, are we seeing igneous activity that obviously precedes the ocean spreading, but it's actually beginning to show places where Gondwana was going to break up? Is there a relationship there, do you think, across these continental margins?
Yes, I think that's the point I was hoping to make with the sequence of showing the ruptures between the continents at the end, which is actually cribbed from Kevin Wong's talk, which he gave to the Society a couple of months ago. At the time, it didn't strike me, because, but certainly when Kevin was giving that example, it did strike me that much of it took place before actual breakup.
Yeah.
But some was much more closely related, and therefore probably came up much quicker.
Okay.
And that's the case in the Karoo, Serra Garal, and Theron Mountains, but it's not the case in Tasmania and the Ferrar Dolerites elsewhere.
Okay, thanks. That fits together really quite nicely, and it makes a nice sort of conclusion to the presentation you've given. So thanks very much for that.
Good. Summer came out, right?
Thanks, Hayden. I've got Liz, then Jackie, then Liz again. Liz Chew first.
Okay. Dave, you showed an amazing U-shaped feature in the landscape. I just wondered, what was that?
It was the results of glacial action on the dolerite. Basically, you'd had a cirque developed higher up, and it's because of the fact that dolerite was fairly coarse grain, it actually eroded much quicker. When essentially a hanging glacier came down, and that hanging glacier has gone years ago.
Oh, I see. I was thinking dolerite is so hard. I've actually been working some dolerite from Cornwall to try and make.
It is hard. Having used a sledgehammer to actually get some of my specimens, I can assure you of that.
Okay, thanks.
Jackie?
Yes, the coal seams that were there.
Yeah.
Did they actually make use of the coal at the base?
No.
Oh,
We were talking, the mountains are actually 200 miles from the base at Halley Bay. Some of the coals were actually burnt, but they were burnt by the Dolerites. It's the first time I've actually seen coal with hexagonal jointing, because of the fact that it was actually burnt by the Dolerites hill immediately above it. It wasn't terribly good quality, but and I think the thickest seam was probably about 1 meter thick. Not much thick, not much less than that. So it certainly wouldn't be economically viable.
right, thank you.
Thank you. Liz Aston, you want to come back?
Yes, another question. Fascinated by these sheer 1,000-meter, I think you said, vertical cliffs.
Yeah.
Are they part of
1,000 feet?
1,000 feet? Oh, sorry.
Yeah.
Are they part of a plate boundary? Presumably they're pretty extensive, are they? These vertical.
No, I don't think so. It's simply the fact that you have got the glacier coming down the front of the escarpment, which has eroded everything in front of it.
Okay.
And then you've got the good fortune of having a very thick dolerite sill, which is very resistant to erosion, which has actually allowed that particular cliff to the northeast of the Goldsmith Glacier to be 1,000 foot high. The cliffs at Lenton Bluff are twice that, and they're also almost vertical.
Yeah.
Not quite, but almost. The highest point in the range is further southwest at Mount Faraway, which is above Coldseam Cliffs. But there you've got much more of a cliff and ledge topography, where the three major sills actually form cliffs, but the sediments between are very much degraded on a 30, 45 degree angle rather than vertical.
Okay, thank you for that.
Any more questions or comments? I can't see any hands up.
Just a comment to say some stunning pictures there, Dave, and absolutely gorgeous looking rocks.
Yes, wonderful.
Did you take all the photographs yourself, Dave?
Yes, except for the air photos and the TAE ones,
Right.
because I'm not that old.
Okay, well, shall we give another round of applause to Dave to thank him? This time with our
Absolutely.
microphones on.
Thank you very much indeed.